Hi students, welcome to Diamond Group of Institutions, NEET and K-CET online classes. So today we are going to discuss dual nature. So in the dual nature, the first topic is photoelectric effect. So already you know about the photoelectric effect definition. That means if the energy of the photon is greater than or equal to the work function of the metal, then electron will be emitted from the metal surface. So that means here phi is the work function. Work function definition is nothing but the minimum energy required by the electron to escape from the metal surface. So either E is the energy of the photon. If energy of the photon is greater than or equal to the work function, then electron will be escaped from the metal surface. So photoelectric efficiency. Next definition is photoelectric efficiency. That means if all the photons should not emit the electrons. That means here what will happen means some electrons may not get the sufficient energy, or some electrons due to the some collisions it may not escape from the metal surface. So due to that one, so the photoelectric efficiency is nothing but the number of photoelectrons emitted by number of photons incidented. That means the ratio of number of photons electrons emitted to the number of photons incidented. So we will get the photoelectric efficiency. Remember this formula. Next topic is the Einstein's photoelectric equation. Already you know about this equation. So now here, if the energy of the photon is greater than or equal to the work function, then electron will be escaped from the metal surface. So that means if the energy of the photon is equal to the work function of the metal surface, just photoelectron will be emitted from the metal surface. So if the energy of the photon is greater than the work function, then the whatever the energy is remaining, first some energy is utilized to escape from the metal surface, and the remaining energy is appearing as a kinetic energy. That means here the kinetic energy, the maximum kinetic energy formula is equal to the E minus pi. That means whatever the remaining energy is there after utilizing for the work function, that is appearing as a kinetic energy. So K max equal to E minus pi. E is the energy of the photon, W is the, sorry, pi is the work function of the metal, and this is the maximum kinetic energy of the photoelectron. So here substitute the values. That means E equal to h mu and pi equal to h mu naught. Here mu is the frequency of the photon, and mu naught is the threshold frequency. If the frequency of the photon is greater than the threshold frequency, then the electron will be escaped from the metal surface and it will get the some motion. If it is greater than, that is if the threshold frequency, yeah, that means the frequency of the photon is equal to the threshold frequency, just electron emit, but it should not get the motion. And the next simplify this one. So mu is nothing but the c by lambda. So h mu is nothing but hc by lambda minus h mu naught is nothing but hc by lambda naught. Either lambda is the frequency of, sorry, wavelength of the photon, and lambda naught is the threshold wavelength. If the wavelength of the light is less than the threshold wavelength, then electron will be escape from the metal surface. Here remember these two conditions. If the frequency of the photon is greater than the threshold frequency, or wavelength of the photon is less than the wavelength of the uh, threshold wavelength. Sorry, just miss. Frequency is greater than the threshold frequency, or wavelength is less than the threshold wavelength, then only electron will be escaped from the metal surface. So the final kinetic energy formula already we know of mv square. So of mv square max equal to hc by lambda minus hc by lambda naught. This is the Einstein's photoelectric equation. Remember this formula. This is the important formula. We can expect the question based on this one in this year. Okay, so now here one more thing is that if the energy of the light radiation increased by the n times, then how much kinetic energy will be increased. Okay, suppose see now just example I am going to tell you. One metal I am taking, the metal work function is 10 electrovolt. So first the light radiation, the energy of the radiation is the 30 electrovolt. So if the energy of the light radiation is 30 electrovolt, then kinetic energy, maximum kinetic energy of the photoelectron is maximum kinetic energy equal to the E minus pi. So E value is the 30 electrovolt, pi value is the 10, then we will get the maximum kinetic energy of the photoelectron is 20 electrovolt. Suppose if the energy of the light radiation is 60 electrovolt, we are not changing the metal, just we are changing the energy of the light. So 60 electrovolt, then what is the maximum kinetic energy of the photoelectron? So maximum kinetic energy equal to E minus pi. Substitute here, then we will get 60 minus 10 is nothing but the 50. Here just we double the energy, 30, initially 30, now 60 means we double it. So now here kinetic energy, see now, initially the maximum kinetic energy is 20 electrovolt, and next to the maximum kinetic energy is 50 electrovolt. That means here the kinetic energy increased by the 2.5 times. That means more than the double. So here if energy is increased by the n times, then kinetic energy will be increased by the more than the n times. So if energy increased by the n times, so then maximum kinetic energy of the photoelectron increased by the more than the n times. Okay, same thing here also applicable. If energy of the light radiation decreased by the n times, so then kinetic energy of the maximum kinetic energy of the photoelectron decreased by the less than the n times. Okay, remember, if it is increased by the n times, so this will increase it more than the n times. If it is decreased by the n times, so this will decrease by the less than the n times. Remember that one. So based on this Einstein's photoelectric equation, we have the problem. So first problem, this problem in your classwork, in your material classwork, class discussion, first problem. The question is, a metal surface ejects electron when hit by green light. That means if the green light fall on the metal surface, it is ejecting the electron, but none when hit by yellow. If yellow light fall on that one, it is not ejecting the electron. Okay, so the electrons will be ejected when the surface is hit by. So some options they given. That means if yellow light fall on the surface, it is not emitting any electron. If green light fall on that one, it is emitting the electron. So see the solution now. So already we know VGR colors. So violet, indigo, blue, green, yellow, orange and red. So from violet color to the red color, the wavelength increasing. Violet color to the red color, the wavelength is increasing. To emit the electron, the wavelength of the light should be less than the threshold wavelength. That means here for green light it is emitting the electron, and for yellow light it is not emitting the electron, means the wavelength of the green light is nothing but the threshold wavelength. So if the wavelength is less than the threshold wavelength, so the surface will emit the electron. If the wavelength is greater than the threshold wavelength, so then surface should not emit the electron. So yellow, orange, red color have the wavelength more than the green color, so it should not emit the electron. So the violet, indigo, blue colors have the wavelength less than the green color, so it will emit the electron. So in the options, if violet, indigo, blue, may anything is there, just see blue is there, so blue is the right answer. So orange, infrared, red light, this should not emit the electron. Okay, now see the second question. This question is in your material home assignment mein sixth question. The question is, a metal surface is illuminated by a light of two different wavelengths. The different wavelengths are nothing but 248 nanometers and 310 nanometers. The maximum speed of the photoelectrons corresponding to these wavelengths are mu1, mu2 respectively. The ratio they given, mu1, mu2 is nothing but the 2:1. First they given the two different wavelengths. Lambda 1 is the 248. So next one is the lambda 2 equal to 310 nanometers, and the next to the given ratio of the maximum speeds, u1 is to u2 equal to 2:1. They only mentioned that one. And the next to something they given HC value is a 240 electrovolt nanometer. This value also they given, and they are asking find the work function of the metal is nearly. What is the work function? We have to find. So this is the given data. Now use the Einstein's photoelectric equation, that is half mv square mass equal to hc by lambda minus hc by lambda naught. So use this equation here. So first case में half m u1 square equal to hc by lambda 1 minus pi. That means first case में the velocity is the u1 and the wavelength is the lambda 1. And on the same metal with a different wavelength of light falling on that metal. So then second equation is half m u2 square equal to hc by lambda 2 minus pi. So first case velocity u1, first case mein wavelength is lambda 1, second case mein velocity is u2, second case mein wavelength is lambda 2. In the two cases we are using the same metal, so work function is the same. Work function is same. Okay, now they are asking find the work function. So now I am doing divide the 1 by 2. If I do divide the 1 by 2, then half m u1 square by half m u2 square equal to the hc by lambda 1 minus pi, hc by lambda 1 minus pi by hc by lambda 2 minus pi, hc by lambda 2 minus pi. Here half m will be cancelled. We will get the u1 square by u2 square equal to the hc value already they given 1240 electrovolt nanometer. Here wavelength also they given in terms of the nanometer. So that's why no need to change this one into the angstroms. So now HC value is 1240 and lambda 1 value is 248 minus pi by HC value is a 1240 and lambda 2 value is a 310. Substitute and cancel it, 248 5 times and 310 4 times, it will be cancelled out. Then we will get the ratio they given mu1 by mu2 ratio 2 is to 1, substitute here. So 2 by 1 whole square equal to 5 minus pi by 4 minus pi. Simplify it, we will get the pi equal to the 3.61 electrovolt. The work function of the metal surface is nearly 3.7 electrovolt. That means 3.67 is almost equal to the 3.7 electrovolts. Like this you have to solve the problem. See the next question, third question. This question in your material home assignment में seventh question. Okay, so the question is a monochromatic radiation of wavelength 640.2 nanometers. So wavelength given, I wrote here lambda 1 equals 640.2 nanometers. From a neon lamp irradiates photosensitive material and made up of cesium or tungsten. Okay, leave it that one. The stopping voltage is measured to be 0.54 volt. So stopping voltage also they given. So whenever they are using this wavelength of source, then the stopping potential is 0.54 volts. Just now they are replacing the source. The source is replaced by an iron source and its wavelength is 427.2 nanometers. So here light source changed, but metal surface they are not changing. Both the cases same photocell they are using. Metal surface is same, but light source, the light which is falling on the metal surface, that light source changing here. Initially the wavelength of the light source is 640.2 nanometers. That time the potential stopping potential is 0.54 volts. So they changed the light source of wavelength of 427.2 nanometer. Then what is the stopping potential they are asking. So now we have the relationship. Okay, so from Einstein's equation we know K max equal to hc by lambda minus pi, that formula. Here one more formula also there. Next we will tell, I will tell you what is the relationship between the K max and stopping potential also. Just remember this formula, K max is equal to the EV naught, here V naught is the stopping potential. So EV naught equal to hc by lambda minus pi. Use this formula here. So in the first case, wavelength is 640.2 nanometers and stopping potential is 0.54 volt. From the equation, EV01 equal to hc by lambda 1 minus pi 1. V01 is the stopping potential in the first case, lambda 1 is the wavelength in the first case. Okay, in the second case, I am writing the equation EV02 equal to hc by lambda 2. In the second case, V02 is the stopping potential in the second case. I am assuming V02 is equal to the V and hc by lambda 2 is the second case mein wavelength, and pi is the same. That means here we are not changing the metal surface, just we are changing the source. So metal work function is same in the both the cases. Now here what I am doing, 2 minus 1, I am subtracting the 1 from the 2. Then see now EV02 minus EV01. So V02 value already I assumed here V. So EV minus EV01. So EV01 value already we know 0.54. I substituted here, and the next one hc by lambda 2, here hc by lambda 2 minus pi, and minus of hc by lambda 1 minus into minus plus pi will do. So this will be cancelled here. So direct I am writing hc by lambda 2 minus hc by lambda 1, pi work function will be cancelled out here. Okay, next in these two we are taking the common as a E, so V minus 0.54, and the next hc value take it as 1242 electrovolt nanometers. Suppose if you want to convert in the angstroms, keep one more zero, that means 12,420 electrovolt angstroms. So here the wavelength given in terms of the nanometers, then I am taking the hc value is 1242 electrovolt to nanometers. So here, and just substitute the hc value in these two cases and simplify it, you will get, the simplification is little bit complicated. Just pause the video and simplify it. Okay, so now for this value, after simplification of this one, we are going to get the 2.9, and simplification of 1242 by 640.2, we will get the 1.94. Okay, so here the value we will get in terms of the electrovolts. So now either E electron, either electro will be cancelled, then remaining is the V minus 0.54 equal to 2.9 minus 1.94. After simplification, we will get the V equal to 1.5 volt. This V is nothing but the stopping potential in the second case whenever we are using the iron source. Okay, so that stopping potential equal to the 1.5 volt. So the answer is the B, 1.50 volt. And to come to the next question, fourth question. Here, this question in your material, home assignment में 12th question. The question is a surface irradiated with the light of wavelength 480 nanometers. So first the wavelength given, I write here the wavelength lambda 1 equal to 480 nanometers. Gives an electron with a maximum velocity v meter per second. Maximum velocity first condition is given v1 equal to the v, I written here. And the with the wavelength, cutoff wavelength is nothing but the threshold wavelength. So that wavelength is lambda not equal to the 600 nanometers they given. Okay, same surface would release electrons with maximum velocity 2v meter per. They are not changing the surface. Okay, so they are changing the source of the light again here also. So to increase the velocity to the 2v meter per second. Okay, here they given velocity 2v meter per second. So what is the wavelength of the light, that we have to find. That means if they are using the wavelength 480 nanometers, then velocity of the electron is v, and if the velocity become double 2v, then what is the wavelength of the source we have to use. And they given the cutoff wavelength or nothing but the threshold wavelength value is 600 nanometers. From the Einstein's equation we know the formula of mv square max equal to hc by lambda minus hc by lambda naught. So use that formula. So here I am writing, so first case में half m v1 square equal to hc by lambda 1 minus hc by lambda 2. In first case velocity, first case wavelength. In the second case also half mv2 square equal to the hc by lambda 2 minus hc by lambda 2. Second case में v2 is the velocity and lambda 2 is the wavelength. That we have to find. Okay, now here substitute the values, first case values, v1 value they given v, hc by lambda 1 I am keeping like this same, why, because some simplification I will do there. So hc by lambda naught here. So v2 value I am substituting here, v2 value they given 2v, I am substituting that 2v value here, 2v square. Okay, so equal hc by lambda 2 minus hc by lambda 2. Just to simplify this equation, so half m 2v whole square means 4v square we will get. I am writing 4 outside, the remaining term I am writing same as half mv square equal to the right side term same I am writing. So now from the first equation half mv square equal to, we got hc by lambda 1 minus hc by lambda 2. Half mv square value substitute in this equation, then we will get 4 into half mv square place में hc by lambda 1 minus hc by lambda 2, hc by lambda 1 minus hc by lambda 2. Right side terms are same, hc by lambda 2 minus hc by lambda 2. Right side left side we have the hc common, then cancel it, then we will get the multiply 4 inside, 4 by lambda 1 minus 4 by lambda naught equal to 1 by lambda 2 minus 1 by lambda naught. We need the lambda 2 value, so 1 by lambda 2 I am keeping same, this send this side. So 4 by lambda 1, here already minus 4 by lambda naught is there, just send the minus 1 by lambda naught to this side. For simplification we will get the minus 3 by lambda naught. Now substitute the values, 1 by lambda 2 equal 4 by lambda 1 value is the 480 nanometers they given, and the lambda naught cutoff frequency, cutoff wavelength or threshold wavelength they given 600 nanometers, and substitute here and simplify this one, you will get the wavelength is 300 nanometers. Okay, the answer is the D option is the right. Okay, like this you have to solve the problems. Okay students, next see the graphs. These graphs are the very important. Already in theory you learned this one. So once again see now the graph between the current and voltage graph. So here on y-axis we are taking the current, and on x-axis we are taking the anode potential. So now, so here the positive is connected to the anode and negative is connected to the cathode. Then if the anode potential increases, then current also increases. At one particular potential, the number of photons falling on the cathode will reach to the, how many number of photons are falling on the cathode, same number of electrons reach to the anode, then the current will be saturated. Okay, now so at particular potential the number of photons falling on the cathode is equal to the number of electrons reaching to the anode, then current will be saturated. And next we have to change the direction, that means connect the negative terminal to the anode and positive terminal to the cathode. Then what will happen, the electrons will move from the cathode to the anode, then anode is connected to the negative terminal, so repulsion takes place and less number of electrons reaches to the anode. Then if we are decreasing the potential, then if you are decreasing the potential gradually, the current also, that means in a negative direction, potential decreases, the current also decreases. At one particular potential, electron should not reach to the anode. At what potential the motion of the electrons stop? that potential is called as the stopping potential. That means the stopping potential is equal to the kinetic energy of the electrons. That means they are not getting the any motion. So now already we know the Einstein's equation K max equal to E minus pi. When the voltage is increasing in the reverse direction at particular voltage, the current will stop. That potential is nothing but the stopping potential. The stopping potential equal to the K max equal to the EV naught. Replace it, we will get this formula. Remember these two formulas. And the next graph is the effect of intensity. So in the wave theory, the intensity formula is nothing but the power per area. But in the particles here, intensity is related to the number of photons. So if intensity increases, number of photons increases. Number of photons increases, number of electrons emitted from the surface also increases. If number of electrons increases, saturated current also increases. So here, see graph here. If so now, this is the I1 and here it is the I2. So if here that means in the second case intensity increased. So if intensity increased, then saturation current also changing. That means intensity is increases, photons increasing, electrons increases, saturation current also increasing. But the intensity does not show the effect on the energy of the photon or kinetic energy of the electron or stopping potential. That's why either stopping potential is not changing, only saturated current is changing. That means intensity will show the effect on the saturation current only, not on the stopping potential. Intensity increases, saturation current also increases. From this I2 is greater than the I1. And the next graph is the effect of the energy. That means if the frequency of the source increases, if frequency of the source increases, energy of the photon increases. Energy of the photon increases, kinetic energy of the electron increases. Kinetic energy of the electron increases. To stop that electron, we need the more energy. So that stopping potential also increases. But if frequency increase, that should not show any effect on the saturated current. That's why for 2 years saturation current is a constant, but stopping potential is changing. Okay, so if energy increases, stopping potential, energy increases, stopping potential increases. So V02 is greater than the V01. So energy of this one is greater than the energy of this curve. And see the next graph, K max versus the frequency, maximum kinetic energy versus the frequency. Kinetic energy, maximum kinetic energy formula K max equal to the h mu minus pi. We have to draw the graph. Take the K max on the y axis and frequency on the x axis. So see now compare this one with the y equal to mx plus c. So here the slope of this graph is nothing but the h. Okay, now if extend here, it will intercept the y axis at the minus pi. That means this minus pi will give the work function. So from this graph we can find the work function of the metal. So at this point kinetic energy, maximum kinetic energy equal to the 0. Why? Because at this point frequency of the photon is equal to the threshold frequency. That's why electron does not have any motion. So maximum kinetic energy equal to 0. And if we take the two different metals, so which one from this graph, which one has the more work function? To find out that one, see now both graphs have the same slope h only, but see here this is the pi 1 and here it is the pi 1. So which one has the more work function means which one has the more y-intercept, that one has the more work function. So pi 2 have the more intercept from here to here on y-axis. So pi 1 has the less intercept. So pi 2 is greater than the pi 1. Okay, next to the graph between the stopping potential versus the frequency. Now write down the Einstein's equation K max equal to h mu minus pi, and write down the K max in terms of the stopping potential EV naught equal to h mu minus pi. From this, stopping potential equal to E, send that side h mu by E minus pi by E. So take the stopping potential on the y-axis and frequency on the x-axis, and compare this one with the y equal to mx plus c mathematics equation, this one straight line equation. So here see here slope is nothing but the h by e. So slope of this one is nothing but the h by e. So here y-intercept is nothing but the minus pi by e. So from this graph also we can find the work function. So but here they will give the value in terms of the volt and send the e to that side, then we will get the pi equal to, suppose here pi by e equal to some 2 volt they given. So pi equal to the 2 electrovolt. From this graph also we can find the work function. So remember all these graphs very important. We can expect the direct question from this graphs also. Okay, now see the photon theory, next topic in the dual nature. So all these are the formulas. Just you can keep the video pause and you can read out all these formulas. You know all these formulas. So here the energy of the light radiation is E, number of photons N. Each photon ka energy equal to the h mu. So this is emitting the some number of photons. So E equal to the N into h mu. N number of photons, each photon ka energy equal to h mu. The number of photons equal to E by h mu. And sometimes number of photons per unit time they will ask. So number of photons per unit time is nothing but here E by T is nothing but energy per time is nothing but the power by h mu. And the next number of photons per time per area. So number of photons per time is nothing but the power by h mu, and the per area they given. So here per area I written power per area is nothing but the intensity by h mu we will get. So next remember this formula also, momentum of the photon E by C or h by lambda, this remember. So if the photon incident to the reflecting surface, perfectly reflecting surface, then initial momentum equal to the final momentum, but in the opposite direction, then change in momentum equal to 2E by C, and the force is nothing but the change in momentum by change in time. By substituting this value here, we will get the 2 into power by C, and the radiation pressure equal to force per area. So write down here force per area, then we will get the formula 2 into intensity by C, or 2I by C we can write. And next, if the surface is perfectly observing, so incident that means incident photon ka momentum is E by C, but totally observed by the surface only, there is no final momentum. Then change in momentum, force, and radiation pressure ka formulas. So suppose general case, if the reflection coefficient they 25% observed, 75% observed they given, then R value. So general case you can write the change in momentum is this formula, and force and pressure. All these formulas you know I written here. So next, if the incident is obliquely, then the change in momentum is 2EC by cos theta. Vertical components will be cancelled out, and add up the horizontal components. Then we will get the change in momentum equal to 2E by C cos theta. Just pause the video and write down all these formulas and tell the formulas. Okay, now see the next question, fifth question in your home assignment, fifth question, that is, so how many photons of wavelength given 660 nanometers should strike on a perfectly reflecting surface in 1 second time period given, so that it may exert the force of 10 Newton, 10 Newton force exerting. How many photons we have to find? Write down the given data, wavelength, time, force they given. So changing the momentum equal to 2E by C formula already we know, but here they given in terms of the wavelength, so write down this formula 2h by lambda. This is the momentum of the one photon. If n number of photons are striking, then force exerted by that n number of photons equal F equal to n into force ka formula, change in momentum per time. So here this value you have to substitute here 2h by lambda, and next time period value is 1 second, so I am not writing here. So now n equal to the F equal to n into 2h by lambda, we have to find the number of photons. Number of photons equal to F into lambda by 2h. F value is 10, lambda value is 660 nanometers. So substitute, and 2 into h value is this one, and substitute. Finally, you will get the answer 5 into 10 to the power of 27 photons. Okay, next question, see now, a monochromatic beam of light wavelength is given. So wavelength is this much, and incident normally upon a surface produces the pressure they given, radiation pressure this much, 5 into 10 to the power minus 7. Assume that the 25% of the light incident is reflected and the rest observed. Find the number of photons falling per second and unit area of the surface. Okay, so radiation pressure general formula I given to you already just now in the synopsis. So I by C into 1 plus R. Here the only 25% of the incident light is reflecting. So R value equal to the 0.25. The formula substitute the value, radiation pressure value, and I by C value we know 1 plus reflecting coefficient of the reflection is the 0.25. Substitute and simplify. You will get the intensity equal to the 120 watt per meter square. Okay, this is the intensity. And next they are asking the question, number of photons falling per second on unit area. That means number of photons falling per area per unit time, that they are asking. So formula already I given to you, I by h mu. So I by mu plus I am writing C by lambda. So I value we know, lambda value we know, and h value we know, and C value. Substitute here. Finally we will get the answer 3 into 10 power 20 per meter square per second. Okay, so the answer is 3 into 10 power 20. So like this you have to solve the problems. Okay, next see the next topic is the de Broglie's hypothesis. This is the wavelength of the photon, lambda equal to h by p. Here photon does not have the mass, so now we can write p equal, already previously we discussed E by C, that is hc by E now. So for material particle, same formula, lambda equal to h by p, h by mv. Here mass will be exist to the material particles, so h by mv, and momentum ki kinetic energy relationship already we know. Substitute here, and this particle will be accelerated by using some potential. So at the place of kinetic energy we can write the QVB. Substitute here, And next, for gaseous particles with respect to the electric field or potential, we cannot accelerate it we cannot accelerate that one. So we accelerate this one by using the thermal energy. So thermal kinetic energy formula is rho by 2 kb T, substitute and get the formula. This is the formula for the thermal neutron. Remember this formula. And de Broglie's wavelength for the electron. Remember this formula. And proton, deuteron, and alpha particle and neutron key wavelength formulas also. Remember, keep the video pause and remember all these formulas. Okay, so next question is the seventh question in your class discussion, fifth question. So here they given electron, alpha particle and a proton all have the same kinetic energy, and they are asking the comparison between the de Broglie's wavelength they are asking. So we know the formula lambda equal to the h by root 2 mk. These are the material particle. For material particles, lambda equal to the h by root 2 mk. So now here they mention kinetic energy is the same. The relationship between the wavelength and mass is lambda is directly inversely proportional to the square root of m. So here mass of the alpha particle is more than the proton, and the mass of the proton is more than the mass of the electron. So this is the relationship for the mass. But they are asking the de Broglie's wavelength comparison. So now the relationship between the wavelength and mass is inversely proportional. So now the relationship we will get this one. That means the lambda alpha less than lambda p less than lambda e. So the option C is the right answer. See the next question, eighth question in your home assignment, material home assignment, fourth question. An alpha particle moves in circular path of radius 0.83 centimeter. Radius they given, radius I written here 0.83 centimeters. In the presence of magnetic field. Magnetic field also they given 0.25 Weber per meter square. So 0.25 Weber per meter square. The de Broglie wavelength associated with the particle will be de Broglie wavelength. So to find the de Broglie wavelength, we need momentum value. So by using this given data, we have to find the momentum. In the moving charges magnetism, we know the radius of the circular orbit. So R equal to mv by bq. From this mv, we have to find mv is nothing but the momentum. So mv equal to the bqr. So we got the momentum. So now find the de Broglie's wavelength. De Broglie's wavelength lambda equal to h by mv. H by mv plus we have to write the bqr. H value already we know 6.62 into 10 to the power of minus 34, and B value, magnetic field they given 0.25 Weber per meter square. Next Q value. So charge of the alpha particle is 2 electrons. That means 2 into 1.6 into 10 to the power of minus 19. Next radius, the radius they given in terms of the centimeters, convert into the meter 0.83 into 10 power minus 2, and simplify it, you will get the de Broglie's wavelength for the alpha particle is 0.01 angstroms. So 0.01 angstroms, D option is the right answer. Now go through the next question, ninth question in your home assignment. 10th question, this is the linear momentum of an electron initially at rest accelerated through a potential difference of 100 volt is. So that means we have to find the linear momentum of an electron. So it is accelerated by the 100 volt potential say accelerated, then we have to find the linear momentum. So for the electron, we know the de Broglie's wavelength direct formula. So de Broglie's wavelength for the electron is 12.27 by root V into angstroms. So now we know the V value, potential difference they given 100 volts, square root of 100 is nothing but the 10, I written here 10 directly. So 12.27 by 10 equal to the 1.227 angstroms. So we got the de Broglie's wavelength, but they are asking the momentum, linear momentum. So de Broglie's wavelength formula lambda equal to h by v. From this momentum equal to h by lambda. H value is 6.62 into 10 power minus 34. Lambda value we got 1.227 in angstrom. Angstrom is nothing but the 10 power minus 10 meters. So now after simplification we will get the 5.4 into 10 power minus 24. Unit is a kg meter per second. These are the problems. Practice seriously. Thank you.